Welcome, as Jim already said. My name is Moritz. Next to me is Fabio, my colleague, who will be giving us a short demo of Hopsworks platform afterwards, after my presentation. This presentation is about the Hopsworks Feature Store and how we manage fast and fresh data for AI at scale using Hopsworks. So let me take a step back and look at how enterprises or companies can actually use AI, or let's say better machine learning, in their business to create value. So on the bottom, or in the first case, you would probably use something we call traditional analytics, where you create at a regular interval, you create dashboards or reports which help guide business decisions. On the next step, you might add some machine learning to this in order to, for example, do more of an explorative or ad hoc research analysis of your data. That can be, for example, a clustering of your customers to better understand your business, and then use that, for example, in marketing campaigns or something like that. In the next step, you actually create or perform actual predictions using a machine learning model, and that's what we call analytical machine learning. So you create predictions ahead of time, so for example, every night or every week, such that then your business can use those predictions, for example, again, to send out email marketing campaigns the next day. Let's say you want to calculate the purchase probability of your customers and then only address those which are highly likely to perform a purchase in your marketing campaigns. The next step would be where you not only perform the predictions ahead of time, but you actually perform the predictions online. And what we mean by that is that you are performing the predictions while the user is interacting with some kind of or part of your product. So he's on a website in the checkout and you want to perform a credit risk analysis at this point in time. In that case, you would do an online prediction. And then last but not least, the most advanced use of machine learning will be real-time machine learning, where you do the same thing as in the operational ML, but you also update your data on which the predictions are performed at real time. And an example for that, a company that is really good at that would be, for example, TikTok, where the things you watch in real time basically go back into the prediction of the next video that is coming up immediately. So now you might wonder, how do, for example, the top two cases differ from each other? And I've already hinted at it. They differ basically based on the input data to your models. Whereas in the bottom three cases, you probably have some kind of batch sources which get updated in a regular interval. In the top two cases, or you will also need to be able to make this data available at very low latency. So for the operational ML, this data might still be updated only at a very coarse-grained interval. But in the real-time ML case, you actually want to update the data from streaming sources, so at real time. And additionally, in the top two cases, you might have data which is coming directly from the application. So for example, which video has the user watched last, or what's the current value of the shopping basket of the user in the checkout. And as you can see with that, also the complexity increases. So your business value increases, but also the complexity. So that's why seldomly you start out implementing real-time machine learning immediately, but it's rather a growth process within the company. And we can now look at the requirements of these different cases, and they're very different. So on the bottom case, we usually care about large volumes of data that need to be processed, and we're interested in versioning the data so that we always have the latest version of the data available, but also be able to go back in time in order to generate our training data in a point-in-time correct fashion, so that we don't leak data from the future into the training data sets that we train the models on. And you care mostly about access to large amounts of data, and you want to be able to reuse those features within the enterprise. So if you have multiple data science teams, so that they can reuse their features. Whereas on the top two cases, the requirements are actually more on SLAs. So you want to be able to guarantee a lookup throughput and latency on those feature vectors and on those predictions, so that it doesn't degrade the experience with the product of the user. And obviously the SLAs also hold for the feature freshness. So you need to be able to guarantee how fast the data gets into the feature store, so it can be served in real time to those users again. So until now, this is only requirements and how the cases look like, but how can we solve them with infrastructure? And actually, we need two very different infrastructure cases for this. The first one, for the bottom case, we usually use a data lake or also a data warehouse to store the data, so we can access large volumes of it. And there's a new term coming up lately, which is called the data lakehouse, which also adds ACID guarantees to our data lake, which gives us properties like data versioning, for example. And technologies you can use for that are Apache Hudi or Delta Lake or Iceberg for this. And for the top one, we actually want to have a LETS data store. And what we mean by LETS is data storage layer that is low latency, high availability, high throughput, and is scalable in storage. And it's very rare that a database possesses all four of those properties. Oftentimes it's only three of them, but actually what you need is the four of them. And as you can see, this is kind of a dual database infrastructure, and that creates another problem of consistency, which adds even more to the complexity of the infrastructure. So now, if we take a step and look how can we solve this with a feature store, it's what we call the offline storage and the online storage of the feature store. However, the storage alone doesn't make up an entire feature store. As we've also seen in the previous talk, we need to build abstractions around these two storage types. And these abstractions help us then, or the data scientists, not only to discover features, but also to train models and in the end, basically put models into production much faster. And some of those abstractions that we need is, for example, or additional data that we need is, we want to collect all the metadata about our features, how they are used, how the data evolves in there. We want to be able to connect to as many data sources as possible and varieties of data sources, so streaming, different data warehouses, cloud storages, Snowflake or Kafka, and so on. We need to process that data, and we want to manage those features, and we can do that with the metadata, so that using the metadata, making it available through search, for example, data scientists can rediscover features and reuse them. And then we have the additional requirements that I've said before. We want to be able to perform time travel. We want to be able to perform validation on the data that is going into the feature store using statistics. And for the online feature store, we want to be able to serve those features at real time, update them with very low latency, and we want to be able to perform transformations on the data. So for example, perform the normalization or perform one-hot encoding when the data is coming from the feature store. So we are in the track of solving the hardest problems at scale of this conference. So obviously we want to solve the real-time case. And how do we do this with Hopsworks? Basically, we rely on 4 pillars. On the bottom, we have our LETS data store, which is called RonDB. It gives us all the nice properties of a LETS database, but we use that database not only as the online feature store, so to serve feature data at low latency, but we also use it to store all the metadata of the entire feature store in it. And because RonDB is in memory and distributed, we can scale it out as much as we want. And therefore, by having all metadata in one place, It provides us with possibilities to implement governance, to unify the offline and online storage, to provide search by syncing the data into Elasticsearch, and to store statistics, for example. And on top of that, we have the API, which is called HSFS, which is then able to guarantee using the metadata consistency and the accessibility. And to tie it all together, we have Hopsworks that provides the necessary services around it to tie everything together. So let us go into the hardest problem. So we want to guarantee feature freshness. And usually what we mean by that is we want to be able, when an event arrives and which leads to an update of a feature, we want this feature to be updated within 20 milliseconds of 200 milliseconds of the arrival of the event. How do we do that in Hopsworks? So we build everything with scalability in mind. And as I said, the main entry point for developers is HSFS, which provides an API in Python, also usable with PySpark, and also available for Scala, Java, Spark. But when we implemented HSFS, we kept in mind that a lot of data scientists also actually like to use pandas. So HSFS is actually agnostic to the engine you're using behind it. So everything works with data frames. These data frames might be pandas data frames, Spark data frames, Spark streaming data frames, or simple Python NumPy arrays. Then the next layer, so when you write data from Hopsworks, from HSFS to the feature store, basically all the data goes through a single Kafka instance. And this Kafka is running within Hopsworks and allows us to decouple basically Spark from the databases. So in order not to overload the database, and it scales in a fashion that we like it, so that we can have, after Kafka, we are having a service called OnlineFS, which is stateless, and we can scale it up and down as much as we want, depending on the workloads, in order to guarantee the feature freshness, which is then upserting the online feature store, which is RonDB. And as you can see, all the layers of this stack basically have access to the metadata, which is also stored in RonDB. And in the second layer, we have the Delta streamer. So we're using Hoodie for the offline feature store, which takes care of taking the same data and upserting it on the offline feature store. So in order to get the backfill mechanism for the offline feature store as well. And all of this is monitored by Prometheus and Grafana. And even if you want to, if you have a service performing predictions, you could log those predictions back to Kafka and also monitor drift and feature drift using Grafana by consuming from that Kafka topic. This is basically the benefit of having all those services within Hopsworks available, so you can easily build things like drift monitoring as well. So now, if we look at how you can use this within HSFS, our API, our SDK, as I've said, everything is based on data frames. So you would usually start out by reading some data into a Spark data frame. In this case, it's some Parquet files. And then what you need to do is, in the first time you want to save features to the feature store, you need to create a feature group. And the feature group is basically an entity or an abstraction that stores the metadata of features which have been engineered together and usually share a common primary key. As you can see, a feature group has a version and a name, a description, a primary key, and a bunch of other properties. You can tell the feature store which column, for example, is the event timestamp, so that you can then later on perform point-in-time correct joins. You can configure statistics, so if you want to compute correlations between features, histograms, or descriptive statistics. And you can set a validation type. So in this case, for example, we're setting a strict validation type, and we're adding an expectation on our customer ID. And basically, if some data will arrive which doesn't fulfill the expectation. The strict validation type will lead to a rejection of the data by the feature store, and it will be logged as an event. And Fabio will show that later in his demo. Yeah, and finally, to save the previously engineered data frame with the features to the feature store, you simply call fgsave with the data frame. This is the first time you create the feature group. The next time you want to ingest data, you would basically swap the create feature group by a get feature group, and then call an insert method instead. So that if you have a job that's running, for example, every night, you would simply get the feature group in a job and then write the engineered data frame to it or insert it to it. This is the batch ingest. We also provide the possibility to mount external feature groups. So for example, if you have some already engineered features in a Snowflake cluster, you can mount them as an on-demand feature group by specifying a query and a storage connector. That gives you access to the features in that storage the same way as a regular feature group does, and you can join them and create training data sets from it. And as I've said, we want to solve the hardest problem, which is also streaming data at low latency. So we need to be able to stream data into the feature store. And it works exactly the same as the batch ingest, but with a streaming data frame, a Spark streaming data frame. So you would, again, you read your data frame from, in this case, a Kafka topic. So you get some streaming data, you perform feature engineering, which is typically some kind of window aggregations. You get the feature group, and then you insert the stream to the feature group. This would be a long-running job that keeps running in the background, basically stream ingesting the feature data into the feature store. And recently, we've also added support to ingest data from Flink, since we couldn't fulfill the latency or the feature freshness requirements with Spark streaming, and also because Flink gives a few better properties for stream aggregations. So you can perform window aggregations in Flink over arbitrary keys, for example, and not only over time. That's why we added support also for Flink streaming, and it's as simple as specifying a Flink Kafka producer, and you can get, again, all the metadata you need to write the stream and sync it to the feature store from the feature group object that you can get previously from the feature store. So we want to show that, yeah, our feature store is the fastest for not only feature retrieval using RonDB, but also for the ingestion. So we performed benchmarks, and this is available as an extensive blog post if you're interested in the details. But basically, we're showing the ingestion of 200 million rows into the feature store over the course of around 80 seconds, and with different width of the feature vectors. So with 11 features, with 51 features, and 110 features, and we show that for 10 features or 11 features, we stay below the 200 milliseconds of ingestion feature freshness to make them available for serving. And even for 100 features, we're able to guarantee feature freshness of below 450 milliseconds. And for the lookup, we can show the same. So we performed benchmark of where we batch lookup 100 vectors per request, 11 features, with a varying number of clients from 1 to 32 clients. And with a simple cluster, which contained only 2 R5 2x large VMs on AWS, we get up to more than 300,000 operations per second with around 7.5 milliseconds P99 latency. So this concludes my part of the presentation, and now Fabio is going to demo the platform.
Okay, thank you very much. Let's see. Can I go back here? Yeah. So wanted to introduce how we do feature, how we can produce feature, and data scientists and engineers can produce features and make them available with extremely low latency to the feature store, both from an architecture point of view, but also from the API point of view. So let's have a look now how data scientists and engineers and operation people can actually interact with the feature store and use it on their everyday job. So in Hopsworks, we kind of group together feature groups, train data set features that belong to the same use case or the same, let's say, department and so on into different projects. So right now I am in the credit card fraud project. I can have a look at a bunch of feature groups that are already available. So these feature groups with the green dot are available online, and they are ready to be used for doing model prediction, so to be able to be queried online. And we do have a pipeline right now that is actually that is actually updating these feature groups that are online. If we look at a specific feature group, for instance, we can look at what are the features that belong to that specific feature group. So we have, in this case, we have the transaction ID, the date time, the credit card number, the amount of the transaction. We do have quite a lot of metadata that are available. For instance, one of the things that we provide is provenance. Basically, we allow, and this is actually tracked behind the scenes. It's not exposed to the API to the user. Everything is done behind the scenes without the user having to even know about it. We basically register which features are being used for creating which trained data set. So this purple dot here is actually a trained data set. And on the other way, we also can show like from which trained data set, if I am a specific trained data set, which feature group it belongs to. I think this is not being shared actually. But anyway, as Maurice was mentioning before, we want to make sure that when data lands in the feature store, it lands clean. We don't want data scientists being worried about like data cleaners and cleaning up data and so on. For that reason, users can define expectations, which is basically a set of rules that need to be defined and need to be passed before data actually gets stored into the feature store. In this case, we have defined an expectation that basically all the transaction amounts should be positive. So no negative values are allowed. And if you get actually a transaction which has a negative value, then an alert is actually being thrown. And in this case, we have configured that everything that fails actually is going to go and it's going to send an alert into a Slack channel. As I mentioned, we do provide a bunch of metadata already in terms of data governance and see exactly which features are being used for which models and the other way around. But we also give the opportunity to users and the possibility to users to produce their own data, also produce their own metadata and attach their own custom metadata. And we do that through these schematized tags, where we basically allow admins to define tags, define schemas, and user to attach those schemas to specific feature groups. So in this case, we define that all the transactions in this feature group are coming from Sweden, and this feature group contains PII information. Everything is indexed. So then, if I want to make sure to know which features are actually using contain PII information, then I can search for it, and it's going to give me back all the results that are available there. We do a bunch of more metadata that we register. We register basically all the activities that happened on specific feature groups. Every time you write something, we remember, and the platform gives you back the number of rows you added, the number of rows you updated, and the number of rows you deleted. And that allows you kind of power the, let's say, time travel capabilities of the platform and have an idea of what happened to your feature store. One additional thing I want to show, as mentioned before by Moritz, everything is, we compute statistics for all data coming in. So that gives a quite extremely powerful tool to data scientists to be able to analyze data and see exactly how data looks like, both in terms of like distribution, in terms of statistics, but actually also having a look at the at the existing data. This is kind of covers the user experience for data scientists and engineers to have a look at it, to kind of keep an eye on the features, be able to work with features, be able to build models, create data set, experiments, and so on and so forth. We do also have an operational aspect of the platform. As was mentioned by Moritz earlier in the presentation, SLAs are critical, especially for feature freshness, if we are building products that rely on machine learning features being available as fast as possible. Everything is being monitored. The application coming in are being monitored by using Prometheus and Grafana, so we can make sure that everything is running. There are no bottlenecks or any issue. And if there are issues, then we can trigger an alert. But we can also have a look at the admin side of the panel, and this is for the operational people. They want to make sure that features land in the feature store within the latency requirements. And in this case, we can see there are nothing being produced right now, but we can see exactly how many features we have been ingested, at which rate, how much time it takes to process those features and write it in the feature store. That allows us to trigger alerts and to be able to notify operation people if there are issues in terms of if the services have problems, or also if the SLAs are being broken, I say. Yes, that kind of covers all our kind of like a quick overview of the platform. We are ready to answer all your questions, and if you have more questions, then yeah, feel free to jump in.